So for those of you that were in my last presentation, this is going to be a very different presentation. There's going to be code in this presentation. There's also going to be a lot faster pace, so you have to listen faster than you did. So hopefully to close out the day, this will keep us all together. So we're going to talk about reactive and fault-tolerant programming at the same time, and we're going to talk about that within the context of Hystrix and RxJava, both frameworks that came from Netflix that do very different things but work well together. Now, as most of my talks are, this is in fact also a microservices talk. And when I talk about microservices, I try to get away from the unicorn and rainbow hype and actually talk about, A, what they can actually do, like we did earlier today, but also what are the challenges that we run into when we start to adopt these architectures, and how do we have to work differently in order to be able to meet those challenges. So let's throw a straw man microservices architecture on the screen. We've got some devices that are talking to some API edge services that are talking to other services that are talking to other services that are talking to databases and other systems and so forth. The question that we have to ask is, how does this change the way that we actually start to write code? In fact, let's drill down a little bit further and think about a specific request. So we've got a phone that needs to display a screen. It's going to talk to some edge API that's going to talk to services and services in the database. How do we write the code to actually do that? Because if I was writing just my typical monolithic Java application, I would probably have some classes with some methods that call into some other classes with methods and eventually go do stuff in the database and send back a response. So let's think from that perspective, okay? Consider a subgraph. So we have just the front-end request, and it's going to go talk to two other services, and at this point, as the author of this API service, we're not even going to think about what's going on beyond the green and the blue services. We're just going to think of them as black boxes. So the natural way for me to write that code, if I were just doing my regular Java application, is I have some request handler, and let's say that we need to return a response of type foo. So we create a foo object, and then we go talk to the first service and get its contribution to the foo object and add that to it. And then we go get the second contribution, and we add that to it. Now that we have the complete foo object produced, then obviously we're just going to return that to the caller. Simple, right? What we do know, based on the code that we're writing, is that the call to service 1 has to actually complete before we get to go make the call to service 2. This is just how our code usually works. And so we're going to block and wait. So even though service 2 has no dependence whatsoever on the call to service 1 to do its work, we're still going to wait on service 1 to finish before we do service 2. Okay? Well, let's drill down even further. We go into service 2, and we realize, oh, well, it's going to also call a service that's going to talk to a database, and then another service that's going to talk to a database. So how do we implement the blue microservices code? Well, obviously, we're just going to create a foo part object, and we're going to talk to service 3 and get the first foo subpart, and of course, we're going to block and wait for that to happen. And then we're going to go get the contribution to service 4 provides and add that. And now we have the foo part, and then that trails up into the foo, and we build the response. Okay, if this is a monolithic application, that probably works just fine. But as soon as we start to introduce network calls for every single line of code that we write, we now have to wait for whatever the latency of those services are. And as the service graph grows and we build more services, we get into this situation where if we don't change the way we write code, things get slower and slower and slower and slower. And what happens when applications get slow? You know, if you build the latest, greatest app for mobile devices and people download it, and after a while they notice it's slow, it uses a lot of data, it drains a lot of battery. What do people do with apps that are slow and use a lot of data and drain the battery? Anybody? They delete them, don't they? And so ultimately, the whole purpose of this presentation is to change the way that you write code so people don't delete your application from their phones. That's literally what we're trying to do. We want to create responsive architectures, but still have the benefit of microservices. Okay, well, obviously I have been being a little bit silly. We all know that we're not going to go write the code that I had on the previous slide because we know how to use futures, right? So we'll create an executor service and we will have our request handler submit the call to service 1 that we've now wrapped in a callable and send that to the executor service, and that job is off running, and submit immediately returns, and we can go do other useful work, right? And so we immediately submit the call to service 2 off to the executor service. So now both pieces of work are running in parallel, and I can add part 1 and add part 2 as they come in. And at this point, it's okay that these gets actually block and wait because we know that we need all of the calls to complete before we can actually return the aggregate response. So now we're happy. This is good. Until the service graph changes. So the way our services work is a little bit different now. We have introduced a dependency between service 1 and service 2. So I now need the result from service 1 to produce the result from service 2. So I submit the call to service 1 to the executor service, but then when I submit the call to service 2, I pass as the constructor argument part1.get. And I'm right back where I started because now I'm blocking and waiting for part 1 to finish before part 2 can execute. And that would probably be fine because one is dependent on the other, except for the fact that I have also now introduced part 3. And part 3 is independent of part 1 and part 2. So I can't submit the call to part 3 until the call to part 2 completes. And so even though I'm using futures, I've gotten back into a scenario where independent work is blocked. Now, we could get fancy and do some of these submissions on other threads, and we could make it work, but ultimately, the fancier the code you write, the harder it is to reason about, the harder it is to keep that correct. Now, fortunately, if we can move on to Java 8, we have better tools. So we don't just have futures, we actually have completable futures. Now, completable futures are much nicer than futures in that futures are not composable, but completable futures are composable. So we use completable futures factory method supply async, and we give it some work to do asynchronously, and here we're just giving it a callable again, so we have call to service 1, but then as soon as we create that completable future, we immediately compose it with something else. We say dot then apply async, and that allows us to supply a function, a Java util function that we're able to immediately apply to the result from call to service 1 when it completes. And this entire chain, this entire workflow that we've just composed executes on a thread and the calls immediately return. So we're now no longer blocking, even though we have built this workflow of call to service 2 depending upon call to service 1. We can immediately then fire off another call, supply async, call to service 3. And so now we're back in the situation where even though we have two workflows and we have some dependencies in those workflows, we're back to where all of the work can execute in parallel, and then we can start to call get on those independent workflows. And at this point, again, we know that we have to wait on everything to complete before we can move forward, so it's okay to introduce some blocking at this point. Now, this gets us pretty far, actually. The problem with it is that the CompletableFuture API is actually relatively low level in that it doesn't give us tools to think about abstract workflows that we typically want to use. If you were in Ted's talk right after lunch, he talked about the ideas of map and filter and so forth. You know, these are workflows that are reusable, that we understand, and that we want to apply time and time and time again. And we probably want to apply them to these service calls. But the CompletableFuture API does not have that kind of interaction. It would be really nice, right, if we could do this concurrency, do this non-blocking work, but then have an API that looks like the Stream API that we find in Java 8. I mean, this is really great. We have a collection of transaction IDs. We turn those into a stream, and then we want to filter that stream down to grocery transactions, and then we want to sort that in reverse order of transaction value. We want to get those IDs and put that in a list that we're going to go do something else with. We invent workflows like this all the time, and yet instead of actually composing the code to do it, we just get to reuse these already composed bits. And so what we really want is a way to compose these service graph workflow interactions and do it in such a way that we're reusing code like this, but that we're also getting the benefit of those calls being non-blocking. And this is where we enter with RxJava. Now, RxJava is just one of many different implementations of the types of things that we're going to look at. The reactive programming ecosystem is actually quite large. You've got things like reactive streams and the reactor stuff that's also coming out of my company, Pivotal. And you've got RxJava 1 versus RxJava 2. There's a lot of things going on. And I love to talk about all those things, but I only have 50 minutes. And RxJava is the one that I know the best, so that's where we're going to go. Now, RxJava is based on reactive extensions that came out of Microsoft, and there are Rx implementations from many different languages. So you've got RxJava, RxRuby, RxPython, Rx, you name it, it's out there. And it sounds complicated. Rx, reactive. It's really based on incredibly old stuff when it comes down to the computer science of it, the software engineering of it. Well, you can trace the roots of reactive programming all the way back to the Gang of Four book and the observer pattern. So what's the observer pattern? Really simple, right? We have this thing on the right-hand side called the subject. The subject has two roles. Role number one is to keep a list of components that are interested in state changes in the subject. And so I have operations to support that. I can register myself as an observer. I can unregister myself. I can say I don't care about your state changes anymore. And so the subject is responsible for keeping up with that collection. And then as its state changes in ways that we care about, it's responsible for notifying that collection of observers. And that's quite simple. Go through the collection and call the notify method on all of those observers. Now, notify obviously is an abstract operation. It's defined on an observer interface, and so we get to implement concretely notify in whatever way we want. And so one notify implementation would do one type of work based on the state changes in the subject. Another implementation might do a completely different kind of work based on those very same state changes. And therein is most of the secret black magic that's going on when we talk about reactive programming. It's based on very, very simple concepts. So what does it look like when we start to do this thing with RxJava? So in RxJava, the notion of a subject is captured in what we call an observable. And we can assign a type to an observable, and I apologize for the confusion on the slide. I have an observable of integers that I'm calling an observable string. I've seen this typo about 15 times now as I've given this talk, and I've failed to correct it every single time, so I get to tell you this anecdote. But hey, we're all human, right? So we have an observable, it's of integers. We're going to use the create factory method on the observable, and we're going to pass to it an implementation of onSubscribe. And the job of onSubscribe is to decide what to do when a subscription comes in. And so what we're going to do in this case is a very simple hello world implementation. We're going to iterate over 5 integers, and for each of those we're going to call subscriber.onNext. That is the equivalent of notify. We are telling the subscriber, who is the stand-in for the observer in the observer pattern, notification 0, notification 1, notification 2, and so forth. And then when we've completed that sequence, we're going to call subscriber.onCompleted. Now this is a new thing that we've added to the observer pattern. The observer pattern does not have the notion of the subject ever being finished. There's nothing more interesting that's going to happen. In this case, observables do have that notion. They can say, hey, I'm not ever going to notify you again. This is the last event that you're going to receive from me. Now, this is a little bit wordy in pre-Java 8 terms. When we get to Java 8, it certainly supports the use of Lambdas, so we can clean up the syntax just a little bit. And instead of passing in an anonymous implementation of onSubscribe, we pass in a Lambda that does essentially the same exact stuff. Now, one of the cool things about RxJava is that if you're still stuck on Java 7 or even Java 6, you can make use of this library. So that is the observable or the subject. Now we're going to implement the observer, or in this case, the subscription. So to do that, we're going to take the observable and we're going to call subscribe. And we're going to pass to subscribe an implementation of observer. And our job is what you might expect it to be. We're going to implement, well, what needs to happen when we're notified? What needs to happen when onNext is called? And so in this case, we're just going to print out what that integer is. We also need to handle what happens when completed is called. When we know that the thing we're observing is not going to emit any more state changes, then we need to decide what we're going to do with that event. And then there's one more event that gets added to the observer pattern, and that is onError. So when something goes wrong, the observable has the ability to pass a throwable indicating what occurred, and we can process that event as well. Now, we can make this less wordy also with Java 8. So in addition to the subscribe method that takes an implementation of observer, there is also a subscribe method that takes 3 arguments. One is an implementation of onNext, the second is an implementation of onError, and the third is an implementation of onCompleted. And then we can chain all this together, so we don't have to break this out into a bunch of different sections of code. We can literally write this as one statement, observable.create, pass in the implementation of the observable.subscribe, pass in the implementations of the observer, and we're done. Okay, so that is the hello world example for RxJava. We probably want to get back to our service graph and understand, well, how does this change our code that we already wrote for futures and completable futures, what does it look like when we use RxJava to write this same code? Well, luckily we get to reuse our callables because Observable helpfully also has a from callable factory. And so we're going to call observable.fromCallable and pass in call to service 1. And then we are going to compose that with another observable using an operator called flatMap. So flatMap is just a special case of the map operation. What does map do? Well, map takes some collection of things and applies a function to every element in that collection. Well, the interesting thing that we see here is that if we call from callable, we're going to get back an observable of foo_part. If I create a function that creates observables from a stream of observables, what would I end up with? I'd get an observable of a foo_part, and that's not what I'm interested in. I don't want to have to peel that thing apart myself. So what flatMap does is compose that stream and then flatten it down into a single observable stream, which is precisely what I want. So I want a call to service 1, flatMap that with a call to service 2, pass in the result. So now I have that workflow running. I want to zip with, what does zip do? Zip takes one result and another result and zips them together by passing them into a function. So we're going to take the result coming out of that first workflow and zip it with the result coming out of the call to service 3 workflow. We're then able to take that, pass that into a Lambda, and if you look at the code for the Lambda, it looks just like the code that we had that was processing the results from our earlier workflow. And so then we just subscribe to this thing, and we're able to do whatever we want. In this case, we're just using the single onNext implementation of subscribe. Now, this is what it looks like using callables. We can actually, again, leverage inline implementations with Lambdas. And in this case, this is one of the few times that I actually prefer the non-inlined implementation to the inlined implementation because this starts to get a little bit wordy. First of all, we're having to tell create what its type is. So you get to do the interesting generic type right after the dot operator, which feels a little bit strange in most cases. We don't do that a lot. And then we have these lambdas in line that do the onNext and onCompleted flow. But ultimately, we get the same result. Now, what does this get us over and above what we've already looked at? Because when I compare what I get from CompletableFutures with what I've gotten so far from RxJava, it really doesn't look all that different. Now, this is normally a 90-minute presentation that I cut to 50. Well, one of the things that had to hit the cutting floor was an overview of all of the rest of the RxJava API. Suffice to say, there is a pretty good equivalent to the Java Streams API in RxJava. And so if you want to compose workflows from these now non-blocking calls, then you're able to do that. But there's another thing that we get that I do need to talk about that we did not get from CompletableFutures, and that is the notion of backpressure. Now, what's backpressure? A lot of different ways that we can define that. My favorite way to define that is the way it's defined on the RxJava wiki. You have a quickly producing observable that's going to meet a slow consuming observer. You know, we're familiar with the notion that things do things at different rates. And so if I have something that's producing at this rate, but then the consumer is able to consume at this rate, well, clearly I'm producing a lot more items than I'm able to consume in the same unit of time. So the question is, well, what happens to all of those other items that I'm not able to consume? Do I overwhelm the consumer? Do I let them hit the floor? Do I put them in a buffer somewhere? Up until this point, we don't really have any tools to make those types of decisions. So a good reactive programming library is going to introduce the notion of tools that allow you to, as a consumer, indicate to the producer, hey, I can only take this much based on how long it takes to process, so please only submit things to me that often. And RxJava has these notions. So when we create an observable, one of the things that we're able to do is indicate what our backpressure strategy needs to be. Now, most of the built-in operators already have backpressure strategies turned on by default, but if I create my own, which is exactly what I'm doing here, I'm creating an infinite stream of integers, and then I'm saying for each of those infinite stream of integers, just omit one of these items. If I immediately subscribed to that for each and then tried to apply backpressure, it would simply ignore me and just keep emitting exactly at the rate that it wants to. So when I add the call to on backpressure buffer, I'm telling it, okay, when you are still emitting items, but the consumer has said that it cannot handle them, just buffer those up to a point. And so when I ask for more, I'm going to start receiving from the buffer instead of receiving from the live stream. And there are many different strategies that we can choose. So that's one side of the equation. The other side of the equation is, well, what do I then do as the subscriber? So in this case, we're going to implement backpressure subscriber, and its job is to, first of all, extend from subscriber so that it can override the call to onStart. And its job in onStart is to apply the backpressure, in this case by calling request10. This is a simple way of saying, hey, please only give me 10 items. That's all I can handle right now. Now, when I request 10, if I never request any more, I'm going to get those 10, and that's all I'll ever see. The producer now knows, hey, I've had backpressure applied, so I'm not going to send this particular subscriber any more data until it's explicitly requested. So my onNext method now has additional responsibility. First of all, its job is to process the things that are coming in, but then it also needs to keep up with, well, exactly how many have I processed so that I can know when I need to request more. So here we have a pretty naive counter implementation that's going to say, hey, if I've processed less than 9 things, we'll just process the next thing that came in. Otherwise, go ahead and process the item, reset the counter, and request 10 more. And if you look at the calls now to process item and request, or these implementations, they're actually quite simple. We're simulating some latency, incrementing the counter, printing things out. When we reset, we set the counter to 0 and say that we're fetching more. So that's what's going on when you look at this right here. Okay, so that's backpressure. Very important piece of the puzzle. So now we can have consumers, based on the work that they're doing, indicating to upstream producers the rate at which they can handle work, and we can start to, again, create some balance in the overall architecture. Let's switch gears. We're a little more than halfway through. What about failures? We haven't talked about that yet at all. We can talk about how we reactively concurrently get stuff. We can talk about how we control the rate at which they're produced. But what happens if I cut there, or there, or there? You know, up until this point, I haven't really created any tools to deal with that. I'm just going to start getting errors, and I get errors from my downstream services. That's going to propagate up to me. That's going to propagate up to my callers, and we have a big mess. Now, fortunately, Netflix has actually written quite a lot on this that's helped educate us about how these things actually work. So this is from a blog post that they published in 2012 that I actually think is still one of the best introductory blog posts on this idea of fault tolerance. So if you look at the top gray bar there, we're talking about the edge of the Netflix API. And at the time, this is based on servlets. So when a request comes into a servlet engine, what's it going to do? Well, it's going to fire up a thread to handle the request. Well, where do all the threads come from? Well, they come from a thread pool. Well, is the thread pool infinite in size? No. So that means we can run out of threads. Now, as long as all the downstream dependencies that this servlet needs to talk to are healthy and happy, we don't run out of threads. But then one of those dependencies, its latency increases significantly enough that at the incoming request rate, and here they're talking about 50 requests per second, all of the threads end up blocking and waiting on this dependency I, and so the threads that are the requests that continue to come in start getting rejected, and so the upstream dependency can't do its work, and this cascades through the entire system. Now, if you take this to its mathematical conclusions, let's say you have 30 dependencies. Those 30 dependencies each have 4 nines of uptime, which is really quite good. That means you have about 4 minutes of downtime on those services every month. There are a whole lot of services that I can imagine writing that I can get away with 4 minutes a month of being down, unplanned downtime. But if we do the math, probability says, okay, well, we have to multiply that 4 nines times itself 30 times, and we end up for our service, not 4 nines, but 99.7, 2 nines of uptime, meaning that I'm down in an unplanned way a little more than 2 hours per month. Now, I can hide 4 minutes. It's a little bit harder for me to hide 2 hours. And so we have to do something about this. Now, the cool thing is that this is based on older wisdom as well. Who's read the book Release It in the room? Okay, a handful of you. The rest of you need to go get this book and read it. What's this book about? How to write software that runs in production and continues to run. Clearly, that's something we're probably all interested in, right? And it is based on the author, Mike Nygaard, friend of mine, experiences that he had working with real customers on these types of problems. Availability, durability, resilience, all of these things. And so he documented some nice patterns. Probably the pattern this book is most famous for is talking about the circuit breaker pattern. I touched on the circuit breaker pattern a little bit earlier. I'm going to go a little bit deeper into it today. So the circuit breaker in this world is going to be a state machine. And we're going to take that state machine and we're going to place that between us and the code that we want to call that's going to make that remote call to another service. In a normal world, circuit breaker's closed. What happens when the circuit breaker's closed? Well, we just execute the code that we're asked to execute. We just make the call to the remote dependency. And as long as that keeps working, everything's great. As soon as we start to hit failures, and failures could mean an exception is thrown, failures could mean that the code takes too long to execute, we have some sort of a timeout. We count all those things as failures, and when we reach a certain threshold of failures and a certain threshold of time, we're going to trip the breaker, and that's going to trigger a state transition into the open state. When I'm in the open state, I execute the same behavior, I make the same call, it's immediately rejected. And in this case, an indication is passed back to caller that says, hey, the thing that you're trying to do is not available right now. You need to figure something else out. And that is the key point. The caller, instead of waiting, trying to figure out, is the thing ever going to return, is immediately told, hey, don't bother, go do something else, and I get to make a decision. Now, if I'm in this state forever, and the service becomes healthy again, guess what? I'm never going to call it again. So I need an opportunity to determine that it's healthy. So we periodically are going to have another state transition. We're going to attempt a reset. And when we attempt the reset, we enter the half-open state. In the half-open state, we behave exactly like we do in the closed state, except we only ever execute one operation. If that operation is a success, we transition back to closed. If the operation is a failure, we transition back to open. And so what you end up seeing is that you oscillate between these two states on the right while it's unhealthy, and then eventually you settle back into the closed state. So this is the machine that is implemented by Hystrix. Now, Hystrix does a lot of other things in addition to that state machine. But again, in the interest of time, we're not going to be able to look at all of those things. So how do I start to leverage Hystrix in my code? Now, I would be remiss to tell you that nothing about Spring Cloud. Because if I were to go use this, I'm going to go use Spring Cloud and Spring Boot to get it done. Now, other people have been here this week that are talking about Spring Cloud and Spring Boot, including my good buddy Josh, who's sick, and I hope he feels better. But you've seen that, so I'm going to talk about how to use the raw framework instead. Again, an old school design pattern. I implement a command object, and in that command object, I wrap the code that I want to execute inside of a circuit breaker state machine in the run method. So run method does something that might fail, and then in this case just returns hello name. So we have that behavior. How do we interact with it? Well, the cool thing is that Hystrix does not prescribe the runtime behavior of my concurrency. I can interact with it in a synchronous blocking way if I want to by calling execute on the command. I can implement an asynchronous way by calling queue, and that's going to hand me back my good old friend future. Or I can interact with it reactively, which is clearly what we're interested in. I can call observe on that command object, and then I can subscribe to that observable just like any other observable that I want to subscribe to. So then we start to think about patterns for using circuit breakers. Well, the simplest pattern is just use the raw state machine behavior and throw an exception whenever I'm in the open state, whenever I see a failure. So this is a toy Hystrix command that you actually pass to the constructor an argument that tells it whether it's going to fail or not so that you can play around with the behavior. So if we pass true to this, we throw a runtime exception. Now that is not the exception that we end up catching when we call run or queue or observe. We actually get a Hystrix level exception that says, hey, this thing failed. There was no fallback behavior provided, so figure out what you want to go do. Which kind of leads us to the second pattern, which is to provide explicitly some fallback behavior. If I'm going to do the same thing every time that circuit is open, why don't I just allow the Hystrix command to specify that? And so if I override the get fallback method, that's exactly what I'm able to do. And so in this case, we're just returning null. This is what we call fail silently. Why might you want to fail silently? Well, let's say that the thing that we're trying to do, this piece of work is actually optional. If you think about, say, Amazon, you go to the product page. That product page is based on about 1,000 different microservices. One of the things the product page does is tell you, hey, people who bought all this other stuff, you might want to buy that too. Is that critical to buying a product? No. So if that service is down, do I still want to be able to buy product? Yes. Well, maybe if that thing returns no data, then we'll say, you know what, just take that off the screen. We won't show that this time. Then you've got notions of static fallback. Maybe instead of turning the feature off, I just want to return the same data by default every time. You can see this in the Netflix architecture. If you're going through a queue of movies, there's always a section that says recommendations for you. Sometimes you look at that list of movies and you're like, they must not know me at all. I would never watch any of these movies. What are you getting? You're getting the default list because the service that provides that data is actually unhealthy right now. And these patterns can get even more interesting. So maybe we have a case where hitting the system of record is our preferred route, But if the system of record is unavailable, we've got this other cache system over here that's a little bit stale, and it's available over the network. Let's hit it instead. Well, that's another network call, and so we want to protect that with a Hystrix command. And so what we end up with here is a Hystrix command that's nested inside of another Hystrix command as part of its fallback implementation. Is that good? Yeah, totally works. In fact, you can nest these things as deep as you want to. It can be Hystrix commands all the way down. Then you've got the pattern of, well, I have a true primary and a true failover secondary version of this service. And instead of there's a switch between primary and secondary in the case of a failure, we have an explicit switch over. When might we want to do something like this? Well, maybe you have a stateful service. One pattern for applying new code to a stateful service is to switch over to the secondary, apply the code change to the primary, switch it back, and then apply the code change to the secondary. Well, during that operation, we don't want to consider that a failure. So we end up protecting that behavior with a semaphore-isolated Hystrix command that's going to make the decision of which service that we're going to call, and then the thread as isolation that we do is actually attached to either the primary Hystrix command or the secondary Hystrix command. So the fallback that we get is actually based on one or this one, depending upon which one's turned on right now. So the patterns get fairly sophisticated in what I'm actually able to do. So to kind of close all this down, let's talk about how we combine RxJava and Hystrix. Let's go back to our implementation using RxJava with Callables. So we remember this. We've got from callable, we send call to service 1, we flat map that with the call to service 2, passing in the result from service 1. We zip that up with a call to service 3. When we change this over to use Hystrix, you'll notice that it doesn't look that different at all. Except instead of saying observable from callable, we're saying new call to service 1 command dot observe. We then flat map that with new call to service 2 command dot observe, and then we zip that with new call to service 3 command dot observe, and the rest of the code is identical. Except now we have all of the reactive behavior, and we have all the opportunity to apply back pressure if we want to, but we have the addition of that Hystrix circuit breaker state machine behavior, and from a readability standpoint, really hasn't changed that much at all. You drill down into the service calls themselves, we're now implementing not Hystrix command, but Hystrix observable command, and that allows me to use the RxJava API directly. And so in this case, I'm constructing an observable instead of implementing a run method. And in there, I actually do the observable.create and do the implementation of onSubscribe. You look at the call to service 2, it is also basically the same idea. We implement Hystrix observable command, except now we have an additional constructor argument that is the foo part that is the result of the dependency from service 1. We implement construct, and we use the dependency to service 1 as part of the onNext call. So that's all of the material that I brought. It looks like we have about 6.5 minutes left. So if there are any questions, I'm happy to try to take those. There might be time for 1 or 2. I can't see. I hope you can.
Hi. Hello.
I can hear you.
have I don't know, maybe a new question. So the reactive thing in reactive fault-tolerant programming in your talk now was to incorporate Hystrix and then be able to apply circuit breaker, or
So
Didn't
the
get that.
reactive part is to be able to do the asynchronous non-blocking calls to the remote services, so I can introduce the concurrency and improve the performance of the service calls. And then the circuit breakers and Hystrix part is to introduce on top of that performance concurrency optimization, the ability to handle failures in a graceful way. So the combination of the two together allows you to address two of the principal pattern or problems that you run into with this decomposition into microservices in a distributed system, in that you can handle the service calls concurrently, but then you can also handle latency and network failure problems as well. Yeah, these questions are like voices coming from the dark. I literally can't see any of you because of these lights.
Hello, my question is, maybe it just looks so, but it looks to me that those two libraries you described, I mean the Hystrix library and the RxJava library, are relatively small. Am I right? Because I mean the functionality presented is just simple observer pattern and well, very simple state machine with only 3 states.
Yeah, so you're right in saying that it looks like they're pretty small, and that is a consequence of having 50 minutes to present the material. RxJava is actually much larger. There's a whole library of stuff that's quite comparable to the Stream API in Java 8 that you can use. And so there's a whole lot of things that we didn't get a chance to talk about over there. And then if you look at Hystrix, there is actually a flow chart on the Hystrix wiki that demonstrates that the state machine that I showed you is a little piece of everything that Hystrix does, and there's all kinds of other things that it can do, such as implement caching, implement different types of thread isolation, implement request batching, and other important stuff. So I was able to show you a piece of RxJava and a piece of Hystrix just to get you interested, but you're going to have to go a little bit deeper dive into those on your own time. Yeah. So maybe one more.
So we've seen the subscriber that might be stateful itself, and who handles concurrency in that? So does the framework ensure the events are emitted sequentially, or do we have to synchronize ourselves?
So there is a default set of behaviors that are kind of built in terms of how the concurrency is set up, and then you have the opportunity to tell it to actually use different executor services or to execute different things on different threads. So you can be kind of as hands-off with the concurrency as you like, or you can actually get very deeply involved with how the threading model actually works. So it's capable of handling either operation mode.
One last question?
Sure.
Okay, we've seen the client example, but where do we really put the circuit breaking configuration, so when it should really open?
Where does the circuit breaker configuration actually live?
In what conditions it should really open?
Yeah, so the circuit breaker obviously lives in my client application, which means that all of the configuration necessary needs to somehow be handed to that application. So if you go to the Hystrix wiki, again, there's a list of about 30 some odd properties that you can set that govern all of the timing thresholds, all of the failure count thresholds, and various other behavior, up to and including the ability to say, I actually want to force this circuit to be open right now so that I can test its behavior and then force it back to closed without there actually being data to drive either behavior. So you can actually get very low level in terms of how these things are tuned. 2 additional points on that. One, there is a great page on the Hystrix wiki that walks you through how do you exactly start the configuration of one of these circuit breakers, and then how do you observe the data coming out of them, because Hystrix is also emitting a metric stream that tells you about the behavior or the traffic that's flowing through that breaker, how to take that data and decide what type of tuning you need to do of those parameters. So that's point number one. Point number two is that you need a good way to deliver that configuration to these apps. Because if you've got 50 microservices, you don't want to have to touch every single microservice to do common tuning. This is where, again, Spring Cloud starts to come into play. You can put a lot of that parameterization in the backing of a Spring Cloud config server and then use that to distribute that configuration in a consistent way to all of the applications. So a couple things also that I didn't have time to cover, but wanted to point that out. So we are officially out of time, so thanks very much for coming, and I hope you enjoy the rest of the show.